All right, we're back. We're on page 124, math analysis. We are talking about vectors, 2D vectors specifically. And now what we're going to do is we're going to talk about unit vectors. Unit vectors are like a huge deal. You use them all the time. They are, in some ways, like the easiest of vectors to think about. So one thing that we've been kind of ignoring, like we know how to find the magnitude of a vector. We know how to find, if you find component form, you get just delta x comma delta y, and then the magnitude, the length, the norm, all three are the same thing, is the square root of delta x squared plus delta y squared. But remember, component form, the order really matters. You have to do terminal minus initial because it has to convey how to get from the starting point to the ending point, so the order matters. So when we talked about direction, right, a vector has magnitude and direction. Magnitude we nailed down like on the first page of the notes. Direction we just stopped talking about because it's like annoying to not have like a really clear-cut way of discussing it, and we didn't really know much about vectors, but now we know enough. So one way to talk about direction is basically to talk about slope, right? Like what's delta y divided by delta x? The problem sort of that has is, if delta y and delta x are opposite signs, you just get a negative slope, and you don't really know, like, should I be going, to the right and down or to the left and up? Like which of those combos should I have? Or if they're both positive or both negative, you just get a positive slope. And then you don't know, are you supposed to move to the right and up, or are you supposed to move to the left and back? You lose something. So slope isn't great. What is great is the concept of a unit vector, though. A unit vector, I mean, if you think about it, unit vector, where have we heard unit before? Unit circle, right? Unit circle has a radius of 1. A unit vector, really similarly, is just going to have a magnitude of 1. So a unit vector is a vector with a magnitude of 1. And a magnitude of 1 is great because it means that it's like the building block that you can build all your other vectors on, right? If you have a vector that has a magnitude of 1 and you need a vector that has a magnitude of 10, just use 10 of that unit vector and you'll have it. So a vector with a magnitude of 1, we can always create. And the way we do it, we've done it several times actually, is we take the vector itself and we multiply by 1 over the magnitude, or we just divide it by its own magnitude. So a unit vector, I prefer to think of it this way. It's a vector divided by its magnitude. So a unit vector. So this is U for unit vector. That's not a universal notation. I'm just using it here. U sub V. So I'm saying it's the unit vector of vector V, is the vector V divided by its own magnitude. So these come up all the time. And often, because their magnitude is 1, it makes all your calculations a little simpler. You don't have to worry about the magnitude. You'll often, like, given a problem, just create a unit vector right away. So unit vectors are a big deal. Also, this is an equation, right? So this thing equals this thing. So you can bring the magnitude of V across, and that'll give you this, which is another of the big ideas. So every vector can be written as its magnitude times its unit vector. That's how we get vectors. So that's an interesting idea. Let's see if we can do these. So we have a vector. We want to find the magnitude of the vector, and then we want to combine that to get the unit vector. Sometimes we know the unit vector and the magnitude, and so on and so forth. All right, so if I see 512, I immediately know 13. So I know that the magnitude of V is 13. But if you didn't know that, you would be doing the square root of 5 squared plus 12 squared, but please don't be doing that. And then the unit vector is going to be the vector divided by its magnitude. So 512 divided by 13. So 5 over 13, 12 over 13. 5 over 13, 12 over 13. So this is a unit vector because if I find the magnitude of this vector, it's going to be 1. So that's what makes it a unit. Every vector that has a magnitude of 1 is a unit vector, right? I mean, they're not all special, but that's what it is. So 724, I immediately think 25 because I memorized Pythagorean triples a while ago. I mean, a while ago in the notes, like I did it like decades ago, I guess. But time catches up with you, man. I don't feel any older, but apparently I am. All right, so which was negative? So we got negative 7 over 25 and 24 over 25. All right, now we can go backwards, right? So if we know a unit vector, which is basically telling us the direction to point, right? You're standing at the origin, rotate until you're facing 3/5, 4/5, and now suddenly walk 14 units. right? What vector do we get? We'll just scale up the unit vector. So this is going to be 14 times 3/5, 4/5. That's a good unit vector. So that's going to be 42/5 and 56/5. I feel like I kind of whistled there. It's weird. I was thinking like, what is it, like Winnie the Pooh? Like, does Eeyore do that sometimes? I don't know. I feel like somebody does that in Winnie the Pooh. Or Rabbit. I feel like there's a lot of candidates for that. I don't think it's a Rabbit. I think it's Eeyore or Tigger. But Tigger just sounds kind of weirder. I don't know. Anyway, somebody let me know. So here, whoa. Look at this unit vector. -1/2, comma, radical 3/2. That feels familiar. I recognize that unit vector. That looks like a point on the unit circle. And I actually know the angle that goes with that. This could be the connection that we were waiting for. So this is going to give me, just multiply this by 10 and distribute. So I get -5 and 5√3. Now what about this? So 6, if I see 6, I think 6√2 because 45, 45, 90 triangle. So I'm going to say the magnitude of V is 6√2, which if you need to is the square root of 6 squared plus -6 squared. So now I'm going to take the vector and divide it by its magnitude. So that's going to give me 1/√2. That's a crazy radical. I have a lot of trouble with radicals and 3s are for some reason challenging on the iPad for me. But if you've ever seen me work in the real world, you will know that radicals are challenging for me there as well. So that's not really new. I'm going to rationalize this because this also looks familiar. Right? This here is theta equals 2π/3. And here, this is theta equals, what is that? 7π/4? Or, if we're feeling fancy, -π/4. So it looks like unit vectors. I mean, think about the name, unit vectors, and we've already mentioned unit circle. It seems like unit vectors are related to angles, and they're related to the unit circle, but they're related to the unit circle in that they're related to angle. I don't really know what the web of contingencies is there. They're all dependent on each other, right? Unit circle, unit vector, point on the unit circle, angle. I'm just listing words at this point. All of these are related. So it looks like, for example, -1/2 radical 3/2 could weirdly have been written as cosine of 2π/3, sine of 2π/3. So it looks like we could actually write unit vectors potentially if we know the angle. We could write them in terms of sine and cosine, and that's weird. But is it weird? Because everything we do is going to come back to that all year. So I'm going to say this is cosine of -π/4, sine of -π/4. I'm doing that for a weird reason that we'll talk about in a second in the next video. But it looks like every single unit vector, new color for this. Every unit vector is a point on the unit circle, which means that we know a ton of stuff about unit vectors because we know a ton of stuff about the unit circle. So this is really interesting. Should I end this here? What's next? I'm gonna end this here. I'll do the calculator stuff in the next video. I was thinking about it here. Like, I don't really know. I'm gonna end here. I'll see you in the next video. We're gonna do some calculator stuff and then move on. So see you there.